We'll discuss another proof technique. This proof technique is proof by contradiction. In a proof by contradiction, we need to consider the negation of the statement. So when we have a statement P, its negation is not P. So in a proof by contradiction, we assume that the negation of the statement is true and show any contradiction. When we show a contradiction, what we're actually showing is that the negation is false. So if the negation is false, then the original statement must be true, because either a statement or its negation must be true, but not both. So the whole strategy for a proof by contradiction is we want to show that the negation is false and therefore the original statement is true. Before we get into that, we need to talk more about negating statements. One concern is the negation of an implication. So if we have an implication, if P then Q, its negation is actually P and not Q, which means we assume the premise and the negation of the conclusion. To prove an implication by contradiction, we negate the implication. So that means we assume that the premise and not the conclusion are true, and we show any contradiction. As in a general proof by contradiction, once we show any contradiction, we're showing that the negation is false, and therefore the original implication must be true. Let's look at some examples now. For our first example of a proof by contradiction, we'll prove an implication. Our strategy is to negate the implication, and when we do so, we assume the premise and the negation of the conclusion, and then we need to show any contradiction. So let n be an integer, and we want to show that if 17n plus 2 is odd, then n is odd. Let's start by assuming the negation. So we want to assume the premise, so that means we're going to assume that 17n plus 2 is odd. And we want to assume the negation of the conclusion. So the conclusion is n is odd. We want to assume that n is not odd, which is just that n is even. So that's the negation of the implication. We assume 17n plus 2 is odd, that's the premise, and the negation of the conclusion, that is, and n is even. And now our goal is to show any contradiction. So let's see what inferences we can make. First, since n is even, n equals 2k for some integer. We want to derive a contradiction. So one thing we can consider is what happens with 17n plus 2. When we do so, we can just do a substitution with n equal to k. So we're going to say that 17n plus 2 equals 17. We'll substitute 2k for the n, and then we'll add the 2. But let's see what happens. We can actually factor out a 2. So here we have 2 times 17k plus 1. When we do so, we can observe now that n plus 2 is evenly divisible by 2. So that means 17n plus 2 is even. It's 2 times the integer 17k plus 1. So we observed that 17n plus 2 is even, but we assumed that 17n plus 2 is odd. This is a contradiction. Because we assumed it was odd. Therefore, the negation of this implication must be false, and that means the original implication, 17n plus 2 is odd, then n is odd, is true. Once again, we assumed the negation of the implication, that was, assume 17n plus 2 is odd and n is even, and we showed a contradiction. And the contradiction happened to be that 17n plus 2 is odd. We showed that it was actually even. Now let's look at another example. And in this example, we will assume the negation of the statement and then show any contradiction. Here, our statement is that the square root of 2 is irrational. When we negate this, we will assume that the square root of 2 is not irrational. Well, that means the square root of 2 is rational. So to start off, we assume the negation of the claim we're trying to show. So we assume the square root of 2 is rational. Now, we just want to show any contradiction to show that the negation is false. Okay, so if the square root of 2 is rational, then we should be able to express it as the ratio of two integers. Where a and b are integers such that b is not 0 and a and b share no common factors. Well, this is useful because if a and b shared common factors, we could just cross them off. We can, for example, if both a and b were even, we could just divide by the 2 that they had in common, and we can do that for other factors either. So we'll assume that a and b share no common factors, or we could just simplify the fraction. So we've expressed the square root of 2 as a rational number, so that as the ratio of two integers, and now we want to see if we can derive any contradiction. One thing we can do is we can consider squaring both sides. So let's square the equation. So we're going to have 2 equal a squared divided by b squared. Okay. Now we can multiply both sides of this equation by b squared. So we'll have that 2b squared equals a squared. Well, now we have to consider what the implication of this is. If a squared equals 2b squared, we know that b is an integer, so, and b squared is an integer. So that means that we can infer that a squared is even. The reason why we can do this is that a squared is equal to 2 times an integer. So when we were to divide that by 2, we'd get no remainder. The modulo 2 would be 0, so we know that a squared is even. And we just proved over the past few videos the statement n squared is odd if and only if n is odd. So if a squared is even, we can make another inference. So if a squared is even, using the statement a number squared is odd if and only if the number is odd, if a squared is even, then a is even. Okay, if a is even, then a equals 2k for some integer k. Okay, let's look at our equation again. Let's consider 2b squared equal a squared again. But now I want to do a substitution with a equal to 2k, because now we know that a is even. So I'm going to do the substitution. I'm going to have 2k squared. So I have 2b squared equals 2k squared. And when I do this, I can see that we have 4k squared. So 2b squared equals 4k squared. And I can simplify this further. We can then infer then b squared equals 2k squared. Now we see that b squared is equal to 2 times an integer, which is k squared. So now we can infer that b squared is even. And then if b squared is even, then b is even. And for that inference, we're just using the same theorem where a number squared is odd if and only if the number is odd. So we actually have a problem because a and b are even, but we assumed no common factors. This is a contradiction. Because if a and b are both even, they must share the common factor of 2. And we assumed that they didn't share any common factors. So we've shown a contradiction, therefore the negation is false and the original statement is true. What's useful about this example is that our contradiction had nothing directly to do with the negation of the statement as our previous example had. Here we just showed a contradiction in the factors that we used to show that the square root, or claim that the square root of 2 was rational. We assumed that we had a simple ratio, it could not be reduced anymore. The square root of 2 is equal to a divided by b, and we couldn't simplify that fraction anymore. But here, we showed that A and B actually would share a common factor of 2, and that's how we came across the contradiction. So once we had the contradiction, the negation, which is the square root of 2 is rational, is false. Therefore, the original statement, the square root of 2 is irrational, is true.